Welcome back, Nature in Code. We're in chapter 6 and we're looking at natural selection. So we just established this simple framework here by which we can calculate the frequency of genotypes in the next generation given their fitnesses. Now, as we know, evolution is the change of allele frequencies. So we're actually more interested in the change of the allele A1 and A2 rather than the genotypes. But of course, now that we know the genotype frequencies in the next generation, we can deduce from that the allele frequency in the next generation. As always, A1 is made up all of A1 alleles, so this frequency contributes directly to the allele frequency. And A1, A2 genotypes are made up half of A1 alleles, so this frequency here of the genotype contributes half of that to the allele frequency. In other words, we can write P here in the next generation as what A1 will be in the next generation, and we now know this is simply P squared times W11 divided by W bar plus half of 2PQ W12 divided by W bar, and so I'm just going to add the 2 here for the half. And so this can be simplified just a little bit by removing the 2's here, which will cancel each other out. And now we have the same denominator, so we can just combine this term here by doing this. Okay, so now that we know P in the next generation, we can calculate the change in P, which is simply, well, whatever P will be in the next generation minus what it is now. And so that is simply this term here, P squared W11 plus PQ W12 divided by W bar minus P. And now if we now implement, or if we replace rather W bar here with this term over here, then this whole thing, so this one here, this whole thing can be simplified, quote unquote, to the following term. And I'm saying quote unquote because it's not really a simple equation, but I'm still going to show you because it's an incredibly important equation. Okay, and this is PQ times P times the difference of W11 minus W22, oops, W12, excuse me, plus Q W11 minus W22. So this whole term here multiplied with PQ divided by W bar, which is, as we've seen above, Q squared, too fast, P squared W11 plus 2PQ W12 plus Q squared W22. All right, so again, I admit this is not the simplest equation. It's quite a beast of an equation. However, it is the fundamental equation of evolution by natural selection. And so I hope that despite its complexity, you appreciate its fundamental importance. Now this we can simplify this a little bit further, but first we have to ask ourselves a simple question. What is it that we're doing here? I mean, why is this so important? I mean, so this notifies sort of, the change in allele frequency, right? This is the change of the A1 allele frequency. And you can, of course, ask yourself, okay, what's the big deal? I mean, if A1 has a high fitness, P will increase. If A1 has a low fitness, P will decrease. Like, what's the deal? Is that really all there is? Is it really that simple? And, to some extent, the answer here is yes, it is really that simple. But on another level, it is not quite that simple, because it really depends what the fitnesses are of the genotypes. That's actually what's really important. And it might not appear that way, but as we'll see in this video and then the following videos, you can get completely different outcomes depending on what the relative fitnesses are of the different genotypes. And so the framework that we'll use to develop this idea is as follows. So we have those three genotypes, right? A1A1, A1A2, and A2A2. And we have assigned to them fitnesses using this W notation. We're going to simplify this now a little bit by saying, well, okay, if we have A1A1, A1A2, and A2A2, we are now going to make two simplifying assumptions. The first one is that the fitness of A1A1 is simply 1. Okay, that's simple. We're just, because the absolute values don't matter anyways, and so we're just going to normalize it in such a way that this one, A1A1, has the value 1. Okay, the other simplifying assumption that I'm going to make now is that A2A2, the other homozygote, has a lower fitness. Okay, and you could of course say, well, but what if it has a higher fitness? Yes, then the exact same rules apply. You could just switch these two alleles. It doesn't really matter, right? The system is symmetrical. But I'm just, for simplicity, I'm now going to assume that this is smaller. How smaller is it? Well, for that, I'm going to introduce this new term S here. It's smaller by S. And we call S the selection coefficient. Selection coefficient. Okay. So how much smaller is the fitness of A2A2 compared to A1A1? That's what the selection coefficient measures. And now I'm simply going to say, well, the genotype frequency of the the fitness of the heterozygote genotype is 1 minus HS. So it is also 1 minus S, but the S first has to be multiplied with this term here, which we call the heterozygous effect. Okay, heterozygous effect. Why? Well, it's because something that only affects the heterozygote. Okay, and that's actually kind of nice, because before, right, we had this system of W11, W12, and W22. So we had 3 variables, and now we only have to work with 2 variables. And so that makes things a little simpler. And actually the simplified equation now for delta P, and again, I have to put simplified here in quotes because it's still not quite simple, but it's a bit simpler, is PQS times PH plus Q times 1 minus H. Okay. And this whole thing divided by the denominator, which is 1 minus 2 PQ HS minus 2 QS. Okay, so again, not super simple, but this is now the fundamental equation, a little bit simplified, and we're going to work with that in the future. Okay, so this is an important equation. PQS times PH plus Q times 1 minus H divided by 1 minus 2 PQHS minus 2 QS. Okay, that's the change in allele frequency for P given its current frequency, given the frequency of the A2 allele, and given these 2 values here, the selection coefficient and the heterozygous effect. Now, there are 3 interesting cases that we will be looking at in the next 3 videos. Based on what we just developed, we can, draw a graph like this. We can say, okay, we're going to plot fitness here. And we have here our 3 possible genotypes, A1A1, A1A2, and A2A2. And we have established that A1A1 has fitness 1. We have also established that A2A2 has a lower fitness, and it is lower by exactly S. Okay, so this is 1 minus s here. 1 minus s. So the question is, what is h? And now h is really sort of the crucial variable here. Because if we choose a value of h that is larger than 1, well then 1 minus hs, right? If we have to multiply here this s with a term that is larger than 1, then this is going to be even lower. So we're going to have a case where it's somewhere here down here. And that's interesting, right? Because now you have this kind of valley here. So the heterozygote now has the lowest fitness. So that's important. Another possibility, so that is just want to write this down here. If h is bigger or greater than 1. The next possibility is that h is smaller than 0. What happens then? So now h is negative. So now you have 1 minus hs, so 1 minus something that is negative times s, so that's 1 plus something. So whatever h is going to be, it means that the term ends up actually being higher or larger than 1, right? Something up here. And now that's interesting too, because now you have the opposite of a valley. You have a sort of a peak, okay? And the heterozygote is now the fittest genotype. And then there's a third possibility, and we've actually already looked at that. That is if h is, neither of those. So h is, on the one hand, positive, so larger than or perhaps equal to 0. And on the other hand, it is not larger than 1. So it's somewhere between 0 and 1. And that means, it's somewhere here in this range. Somewhere here in this range. Okay. And so what you have here is kind of just a slope, right? A fitness slope, where the intermediate, A1, A2 has an intermediary fitness. It doesn't have the lowest fitness, which would give you this valley. It doesn't have the highest fitness, which would give you this peak. It has an intermediary fitness, so it gives you this kind of slope. And so these three cases are all fundamental, because in the case of this fitness slope, what we have here is so-called directional selection. Okay, and I'm going to put this here in green. Directional selection. It's a specific type of selection. Now, if we have this peak, we call this balancing selection. And finally, with the valley, where the heterozygote has the lowest fitness, we call this disruptive selection. And now when we're going to implement this in code, we will see that these have very, very different dynamics and very different outcomes. And so, one way to think of this, and this is why I use these terms, is sort of as a fitness landscape, where, in one case you have a peak, in the other case you have a slope, and in the third case you have a valley, right? There's really only these three possibilities. And these three possibilities, though, it turns out, have very fundamental outcomes. And in the next couple of videos, we will implement these dynamics. So see you in the next video.